Welcome back to the Quantum Science Seminar. Today, it's all going to be about photonics, and this is episode 7. To remind everybody, and for people who haven't seen this before, we do take questions. Please send your questions to quantumscienceseminar@gmail.com, or you could use the YouTube live chat at the right or at the bottom of the screen. We are going to start answering some of these questions roughly in the middle of the talk. So if you have any, please go right ahead and send them. And then we will answer the rest of your questions at the end of the talk. Our speaker today, Cristiane, has kindly agreed to answer all of the questions in short written form. So if we have more questions than we have time for, don't worry. We will upload that onto our website and you will be able to get an answer. Please also note that there is roughly half a minute time delay between what we're seeing and between what you're seeing on YouTube Live. And with that, I'd like to hand over to Andrew Daly, who is going to introduce our speaker today.
So welcome everyone, and it's a great pleasure today to introduce our speaker, Cristiane de Morais Smith. Cristiane is originally from Brazil, where she did her PhD with Amir Caldera, also in collaboration with Johnny Blatter from the UTH in Zurich. And since 2004, she's been a full professor in the Institute for Theoretical Physics at the University of Utrecht in the Netherlands. Cristiane has pioneered many new directions sort of across solid-state physics, strongly interacting electronic systems, also AMO systems and cold atoms. And she's won numerous awards for her work, including in 2016, the Dresselhaus Prize of the CUI in Hamburg for her outstanding contributions to the understanding of topological phases in two-dimensional atomic and electronic systems. Cristiane, as I say, has contributed a lot across solid state and AMO systems, and some of these things I think will be combined today. And Cristiane, we're really looking forward to your talk on quantum fractals.
Thank you very much, Andrew. It is a great pleasure to be here. Hello, everybody. Today I'm going to tell you about quantum fractals. The first part of the talk will be about statics, how to realize a quantum fractal with an STM structure. And in the second part, I will tell you about photonic systems which allow us to understand dynamics in these fractals. Unfortunately, I had a very ambitious abstract wishing to talk also about time glasses, but I'm afraid I'm not going to get there. Okay, so the concept of fractal. Fractals are closely related to humans and nature. If I go to the market to buy Romanesco broccoli, I will find a beautiful structure that when I look at its parts, I see that it's self-similar. It repeats itself on different length scales. If it's a winter day and I can look at the structure of the trees, at the branches in the trees, I will also see a fractal structure. Underneath, there is a beautiful hidden structure in the roots, which is also fractal. If it's a spring, I can see some leaves, and they are also fractal. So fractals are not only around us in nature, but also inside ourselves. Our lungs have a very fractal structure. Our intestines, our circulatory system, the neurons have also a fractal structure. But all those are fractals in space. But there is also something else that are also fractals in time. Actually, if you look at the heartbeat dynamics, you will see some self-similarity. And it's extremely important for being healthy. If your beating dynamics becomes completely ordered or completely disordered, it means you are seriously ill. So in a trial to imitate nature, humans have been designing structures with fractal shapes. For instance, one of them are antennas. You can see here a Koch curve, or the so-called Sierpinski gasket. If you build antennas with fractal shapes, it's extremely convenient because you can send and receive simultaneously large and short frequencies because they have different length scales in themselves. For making solar cells, they are also extremely convenient, because if you increase the complexity, you see here in blue, if you increase the complexity of the fractals with which you are patterning your 2D structure, you can store more and more energy. But they are not only in science and nature, they are also in arts. Here, this is a beautiful tiling system in a church in Rome from the 11th century after Christ. You can also see them if you go to the Escher Museum. This is a beautiful structure that is the preferred one by our friends studying ADS CFT because of the horizon, or in more subtle structures like in a Pollock painting. This is more hidden, but it's also fractal. So one of the things in the concept of fractals is the property of self-similarity. Although fractals have been used for long, they started to be understood and classified only last century due to this very important work of Mandelbrot. So here you see the image of the Mandelbrot set, and as you zoom in, you always see the same structure. This also holds for the Koch curve, which is the one that is making snowflakes. So if we look here at a Sierpinski carpet, this is a square in which I divide it into 9 squares, and I take out the central one. Then I take each of these 9, and I divide again in 9, and I take out, and so on. So if I zoom in into this red square, I get this big structure, which is self-similar to the previous one. And when I zoom in into the red square again, I see again the same thing. So they have this property of self-similarity. The second important property that fractals have is that they have a fractal dimension, or Hausdorff dimension, which is not an integer. So let's look here at this example, which is the Sierpinski gasket. It is a triangle. In the middle of it, I draw another inverted triangle that I take off. I will remain now with the 3 triangles. In the middle of this one, I draw another inverted triangle that I take off. I remain with 9 small blue triangles. I take the central part, and successively. And this structure has a Hausdorff dimension of 1.58. What does this mean? This Hausdorff dimension is defined as the log of the number divided by the log of the scaling. Let me show you how this emerges, this number 158. Suppose you have a straight line. Now you use a scaling 2, so you make this straight line twice as large. This is the scaling, which is here, this 2. Now you ask yourself, how many of the original line you can plug inside? 1, 2. The number is 2, because you are in 1 dimension. Take now this red square. Now you scale the y-axis by 2 and the x-axis by 2. The scaling is 2. How many of the red square you can fit inside? 1, 2, 3, 4. The number is 4. The dimensionality is 2. Take a red triangle, paint it completely red, and paint this one completely blue. If you now take this red one and you scale it by 2 in this direction and by 2 in this direction, and you ask how many of the original red triangle you can put inside, to cover the entire blue surface, it would be 1, 2, 3, 4. The number would be 4, it would be in 2 dimensions. But you have a Sierpinski gasket, so you have to take away the central one. So you have only 3 times the same structure. And now log 3 divided by log 2 gives you 1.58. So all the fractals, or most of them, there are some exceptions with integer dimensions, but a characteristic would be a non-integer dimension. So another interesting feature of a fractal is that they are connected to quantum chaos. So we have a friend who told us last century that God does not play dice with the universe. But I keep wondering whether this is really true. So let's do what is called a quantum chaos game. And now what I am going to do is the following. I am going to build a triangle. We will draw a triangle, and now I have 3 vertices in this triangle. I am going to call vertex 1, 2, and 3, but because all the dice that I have to play have 6 numbers, I will call this also 1, 2, 3, 4, 5, 6. So every time I play dice and I get number 1 or 4, I come to this vertex. 2 or 5 here, 3 or 6, I come here, okay? So now we are going to choose a random point inside this triangle and we play dice. And we will get a certain number, let's say 1. So we will trace a line until that vertex and pick up the middle point. And every time after I do this, I repeat the procedure. I play dice, I get another random number, I join the point I was with this vertex, and I get the middle point. So let's look at it. A random point, I play dice now, I got 2. I pick the middle point. Play dice again, I got 1. Pick the middle point. Play dice again, I got 2 again, middle point. And I play 1,000 times. And I start getting lots and lots and lots of points inside this triangle. And after many times playing, I get this beautifully ordered structure out of a completely random game. So since we have fractals everywhere in nature and in our body, I keep wondering whether God doesn't play dice with the universe. Okay, so all these fractals that I told you about until now, those are fractals in the classical world, but there are also fractals connected to the quantum world. The first example that would come to our mind is the Hofstadter butterfly. So if I have a 2-dimensional lattice under a perpendicular magnetic field, I will have a structure for small fields. Those are the so-called Landau levels. And if I plot now the energy levels as a function of the flux, what I will see that actually the bands are going to be the black structures and there are gaps in between. And these gaps, they are characterized by a quantum number, which is nothing than the Chern number or the Hall resistivity. So it's connected to the quantum world, this beautiful structure in a way. In Anderson localization and quantum turbulence, there are also fractal structures that emerge, usually multifractal structures, but those are not fractals in real space. So the question is, we would like to first understand how electrons behave in fractal dimensions. And you would say, what the frac? So that's the work that we did last year, and I am going to tell you about. But before I tell you about this work, let me tell you a little introduction on the history of STM manipulation to build artificial structures. So what are we going to do? Everything started with this beautiful work by the group of Don Eigler in 1993, when he took the surface of copper 111 and he started patterning iron atoms. You see here, this is iron patterned on copper. On the surface of a metal, you have a 2D electron gas. And when you pattern now a circle, you will get quasi-particle interference and you will see that the electronic wave functions are forming this beautiful structure with maxima and minima. He called this a quantum corral, since we are seeing wave functions, not the sea making these waves. But it took almost 20 years until the group of Hari Manoharan decided to build a lattice using the same technique. So this is a beautiful pioneering work in the group of Hari, where he is now taking the copper surface, so this is the yellow, and he is getting adsorbates. These are carbon monoxide molecules, which are the brown ones. And now what he's going to do is with the tip of the STM, he's going to move this carbon monoxide one by one in a way to form a triangular lattice. So when he does that, the electrons are going to be expelled by the regions where the triangular lattice is. So the electrons are going to form a honeycomb lattice. As you can see here, it is a very clear and beautiful structure. And if you now look at here I'm showing you the structure. Let me get the laser pointer again. If I don't tell you that this is 2 nanometers, you can't distinguish the local density of states for this artificial graphene lattice from a true graphene lattice. And when you look at the GIGV, you also see this V shape, which is characteristic of the Dirac cone. So it is a marvelous way to build an artificial lattice. So we took over from this point, and our question in the very beginning was, you are putting the COs here in the black spots in this structure because you have to put COs on top of copper. And the underlying copper lattice is triangular. So the first question we had is, can we only build triangular lattices? Because if this is the case, we can't go very far. So the first trial that we had in 2017, it was to use this technique to build a square lattice. And we have built a lib lattice, and indeed we have shown it's possible to build any geometry with this lattice. And last year we have been showing how to control orbital degrees of freedom and how to separate, to build a lattice with px and py orbitals and separate them in space, define a certain site will get only px, another site only py or both, and then to also separate them in the energy scale to be able to get, for instance, the equivalent of the Zeeman effect, how you separate spin up from spin down. Here we separate px from py. That's the second paper here. Then we went on and we built several Kagome lattices in a way that the hopping in the last triangle is weak or strong, to prove how to build zero modes in the corner of this Kagome lattice. It is published here also last year. And then we went on to build Kekulé structures with different terminations to understand how are these topological states if you would have different terminations in the lattice, because for topological crystalline insulators, this defines the unit cell and it changes depending on the termination if the state is topological or not. This one is in print in PRL, but it's also an archive. So we have been using this technique to build a variety of systems, but today I want to tell you only about the electronic fractal that is built with an STM. And in all the previous works that appeared on the last page, there are many collaborators, but I want to mention you just a few of them who are the most prominent ones. So Sander Kempkes, he is my PhD student who has been doing the theoretical calculations for most of these works. And then there is Ingmar Zwart, who is the STM specialist in Utrecht, and Marloes Lot, who was his PhD student, who has been doing all the measurements in this previous work. So today we are going to concentrate on building a fractal. So how can we build a fractal? Here I start showing you the structure, how we are going to do that. In orange in this picture, you are seeing the copper atoms, and then in black, you are seeing the carbon monoxide structure. We are going to arrange them in that way with the hope that the electrons get confined to the red, blue, and green dots, as you see here. And if this is the case, we are going to form a Sierpinski triangle. Please notice the separation between two COs is 1.1 nanometer. We are doing patterning on the nanometer scale. Okay, So that's what we are going to build, a first, a second, and a third generation of a Sierpinski fractal. Here you see the constructions. This is the topographic image from the STM, and these are the blacks are the COs. This is first, second, and third generation. And we are going to characterize these structures using muffin tin and tight binding. So let me tell you what this is. The muffin tin model. So it's all about cooking. Here you see a tin to make muffin, to bake muffin, inverted inside another tin. So actually the carbon monoxide molecules are like these little mountains that you see here. And the 2D electron gas will be flowing in between this mountain structure. And in our case, the mountain structure is given by the COs, which are arranged in a certain way. We know the effective electron mass, we know the effective diameter of these mountains, we know the height of these mountains. We can solve Schrödinger equation for a certain configuration in the continuum. So this tells us basically the same thing what the experimentalists are constructing. Then we can see the energy structure for this continuum model, and out of that we can map into a tight binding description and find the nearest neighbor and next neighbor hopping parameters. So it's all single particle, no interacting physics here, okay? So we do that, and then we do the experiments. When you do the experiments, here you see the third generation Sierpinski. You will now place your tip on the red, the green, and the blue sides, and you take the spectra. You measure the GI/GV with the normalized by the GI/GV without COs, and you measure it as a function of voltage. And then you do now the muffin tin, the tight binding, and you look at the spectra that you get. So you see that you can reproduce the main features in this spectrum. So now what we do, we look at some values of energies where there are some interesting features. For instance, at minus 300 MeV, all the three, red, blue, and green, are equal. At minus 200 MeV, the red is low, but green and blue are high. And at around minus 100, red and green are high and blue is low. So now what we are going to do, we are going to fix ourselves at a certain energy. The first one is minus 300 MeV. The second two plots are minus 200 and minus 100. And now you scan the entire sample and you look at the local density of states everywhere at that fixed energy, okay? You do the maps. So basically what is being plotted here in this yellow and white color, it's the modulus of the wave function square, modulus of psi square. It's the wave function maps. Light color means very high intensity and the dark colors means low intensity. In the upper layer here, you have the experiments and underneath you have the theory. So you can see there is a beautiful, clear Sierpinski gasket here at minus 300 MeV. And at minus 200, the structure starts to partition. And at minus 100, we have this anti-bonding configuration. So here it's the bonding, here is in the anti-bonding, and here it's something in between. So this, all what I'm telling you here, it has also these maps in 3 dimensions where you can see the height of the peaks. These upper pictures now are theory and the lower pictures are the experiment. It agrees very well. So now the most important question that we want to answer with this work is, do the electrons understand that they are living in a fractal dimension? Do they see the non-integer dimension? So to answer this question, we can use a method that's called box counting or Minkowski-Bulligand method, in which you will start covering the surface, which is shown here in white, by circles or boxes. So the idea is the following. You take a circle that has a reasonable size compared to the surface that you want to cover. You would not take a circle of this size, otherwise you don't see anything. You take a circle, for instance, of the size like the pink one here, and you take many of them and you cover everywhere the white parts. And then you count, how many did I need? 1, 2, 3, 4, 5. And then you plot the log of the number versus the log of the inverse diameter of this circle. And you will get a point. Now you change the size of your circle, you make it smaller. You cover everything again. You will need more circles to cover everything. You count again the number, and you plot again the log of the number versus the log of the inverse radius. You get another point. And you keep reducing the size many times, and you keep increasing the size. And you will get a set of points. And the set of points lay down in a straight line. And the slope of this straight line tells you the dimensionality of the surface that you are covering. And here we would get 1.59, which is quite nice because the mathematical Sierpinski gasket is supposed to have a dimension 158. So we can do that not only for the minus 300 electron volts map that I had shown you before, but for many, many, many other maps that we have. And you will see that for all of them, you will be around 1.6. So now when you look at these curves, you see some error bars. What is the meaning of this error bar? So if you go back here, I told you I am covering all the white parts with the circles. But what about this point? This is gray. It's not really white. What is white? You see these white parts here, or gray parts, they are peaks in 3 dimensions, which have been projected. And depending on the height, it's more white or less white. But how to set up the threshold for what is white? You could say, okay, take the highest peak and say that everything which is above 90% of the highest peak is white. You would get one boundary of these error bars. But if you would be more generous and say, no, I want to call white everything which is up to 60% of the highest bar, the highest peak, then you would have the other bar, the other limit of this error bar. Whatever you take, you can see that you are really around 1.6. And this is very different from what you would get if you would do the same exercise in graphene, which would be around 2. So it seems that we are around 1.6, except here that we have a lower dimension. This is the antibonding, which also does not look much like a Sierpinski. In the antibonding region, we are at a dimensionality lower, it looks like. But in general, there is a trend. So the electronic wave function knows that it's living in a fractal. That this works for the third dimension, for the third generation, sorry, not third dimension, third generation, it's okay. But for our surprise, it also worked for the first and the second generation. This is the data for all energies in red and blue. So even for the very tiny triangles that has a hole in the middle, the electrons already know the fractal dimension. That was very surprising. So let me now conclude the first part. We have been experimentally building a Sierpinski fractal and investigating the electronic wave function in this fractal, and we could conclude that it is seeing the fractal dimension. I didn't show you in detail, but I would like to keep here the references in case you were interested. Also about how to build a Lie lattice and control the orbital degrees of freedom, or how to investigate topology in an electronic hottie. So I would like to make a break now here and let you ask me questions about the first part before I enter into the dynamics in the fractals, if you have some.
So thank you very much, Cristiane, for the very interesting talk so far. So we have a couple of questions that have come in. The first of them is from Callum Duncan, and he asks, by understanding the physics in fractal systems, can we say something of the physics in multifractal systems?
Yes. So actually, for instance, one of the things we have been checking, that has been a project of one of my master students, and his thesis is available. You could check whether this is truly a fractal and not a multifractal. Okay, so we have been proving it is really a monofractal and not a multifractal. I would say yes. We have means to identify the features of a multifractal, and we can at least distinguish whether this is truly a multifractal or not. We also did, for a multifractal, we also did the box counting, and you can agree that it is a multifractal. So it's possible. If you send me an email, I can send you the thesis by PDF. Yes?
So then we had a second question in two parts from Didi Leibfried, and he asks, what happens in the triangle game that you showed before if you start in the excluded central triangle, and sort of as a follow-up, do you then paint the regions that were untouched in your original example?
Yeah, that's very interesting. It still works perfectly, because you see, your initial point does not need to be part of your Sierpinski. And when you play your dice, what you will take is the middle point between your initial point and the vertex that you got. It even works if you start outside the triangle. You can start outside the triangle, play the game, and then, of course, if you start very far away from your triangle and you pick the middle points, you will start counting the points which are only the ones which are inside the triangle, but even that works. You can start outside and then you disregard the points outside, and from the moment you get inside, you will form a Sierpinski. You can find this also on YouTube. If you play around, you can find images of that.
We have one more question that's just come in from Yiming Pan, who asks if there's a difference when you're defining and thinking about fractal dimension between considering wave functions and considering the wave function squared, so the density distribution.
Yes, that's a very important question. You see, everything what I am telling you is only for the modulus of psi square. I don't have a resolution to know the phase. Unfortunately, that's what we can access. It would be wonderful if we could, on top of it, see the phase of the wave function inside this fractal. We could manipulate much more and build even more interesting stuff. Yes, everything is modulus of psi square.
Do we expect there to be a difference in the properties depending on whether you're considering the wave function or the modulus squared of the wave function in that sense?
Not for this experiment, but if I would like to put gauge fields, for instance, and then I should be able to control the phases, that would be great if I could. You see, in the moment when you are interested in topology and you would like to have gauge fields, then it would be very nice to be able to see also the phase and to have this parameter at your disposal to manipulate. But unfortunately, we still don't have it.
Okay, thanks for that, Cristiane. We'll take more questions at the end. For the moment, we'll move on to the second part. Looking forward to it.
Very good. So now I come to the second part of the talk. And this is a collaboration with my colleagues from China. It is a group doing now quantum transport in photonic systems. Is the group of Professor Shen Mingjing. And together with him, I was visiting last November because I am a member of the Tidjali Institute. And for long, I have been a member of the Utrecht Quantum Center, which are now both at the Shanghai Jiao Tong University. And there I got to know their work on photonic lattices, and I got involved into it, and our paper has just appeared today on Archive. So now we are going to talk about the quantum dynamics in fractals, and I would like to show you the photo of Chao Yun-Chu. She is the PhD student of Shanmin, who did most of all the measurements, helped by some colleagues. Okay, so here is the archive number. It's going to appear tomorrow. And I think we could rephrase the question that we are going to study now as, how would a quantum ant behave in a labyrinth? So the problem of the ant in the labyrinth has been interesting many researchers a few years ago, in the 80s, especially Dejean, who called it the ant in the labyrinth. That's the name of the problem. And they have been looking how an ant would move into some percolation network, for instance. It's the issue of classical diffusion in a fractal. And people have been studying and studying how would be the diffusion exponents in this problem and so on. But we didn't have access to quantum diffusion at that point. So now what I'm going to tell you today is about that. How should be the quantum ant in the labyrinth problem? So the problem that I told you that we have been building via atomic manipulation and building the Sierpinski fractals, these structures, they are static. There is also a beautiful one that was proposed in Nature Chemistry in 2015 by doing molecular assembling, which is again another static structure. Or you can also do, using some photorefractive material, you can also get some fractals, again static. But now we are interested to detect dynamical properties. And for that, we have to go to photonic systems. So using femtosecond laser direct writing techniques, they have been showing before how to build very well-defined lattices, regular lattices. So now here we are going to do that. And so first, before, let me show you one more work of the group of Chanin, where they have been doing quantum walk in 2 dimensions in a regular lattice. You see here, you see the wave guides, they extend along the z-axis, and you see a square lattice by this region. Let me get the laser pointer again. So you can see here the wave guides in the z-axis, and if you look at the cross-section, you will see a square lattice. And if you now would inject light in the very center of your square lattice, you would see ballistic transport in the log of the variance versus log of the length along this direction, which is the same as time, because along the wave guides, the photons are propagating just with the speed of light. So if you build several ones with different lengths and you detect them, you are detecting them at different times. You would see just ballistic transport going with z square. Now, the question is, the sigma squared goes with the t square. How should this change when we have a fractal? So we are going to do then a photonic lattice device. You see here the wave guides, but now the structure is a Sierpinski gasket where you just take away parts of it. So the cross-section is going to be a Sierpinski gasket. Here you see the white dots are the waveguide array, and these white lines, they don't mean anything. It's just a guide to the eye for you to see the formation of the Sierpinski triangle. This is a 4th generation Sierpinski triangle, but from the point of view of the photons, it will be a 2nd generation. This is because the photon, if you inject it here, it will propagate along this waveguide, but it will also hop to the neighboring sites in a quantum process, just by the quantum mechanics wavefunction overlap. And then when it is here, it can also hop to these sites. So this little void here does not mean anything, because any nearest neighbor site is connected by hopping, okay? So the first hole that the photons are going to see is this big one, and then the bigger one. Very good. So Now we are going to have quantum transport, is a continuous time quantum walk. The wave function is going to be governed by a certain Hamiltonian. So the wave function is the combination of the wave functions at all the sites j, going from 1 to n, with a certain amplitude aj, and the modulus square is what I call pj. And now the Hamiltonian that is governing the evolution after the first site at time 0, the site is 1, is going to be simply a tight binding Hamiltonian, where now this hopping is restricted to be on a Sierpinski fractal. Okay, so we are going to build 3 types of Sierpinskis. So the first one, three kinds of fractals. Turns out to be all Sierpinskis. The first one is the Sierpinski gasket that you have already seen, that has a dimensionality 158. The second one is a Sierpinski carpet. The Sierpinski carpet is a square. I divide it into 9 little squares, take away the central one, take the next one, divide in 9 and take away the central one, and so on. And now this Sierpinski carpet has dimensionality 1.89, because if I take this first one and I scale it by 3, I will remain with only 8 of the same. So it's log of the number, which is log 8 divided by log 3. But in addition to the Sierpinski carpet, we are also going to look at the so-called dual Sierpinski carpet. What is this? So you see, this is the first generation. That's the second of the Sierpinski carpet. Now I will take the central point of this little square there, and I will make a lattice point associated to it. So the next one is another point, and then it comes around, okay? So I associate one dot in the middle of this filled square. And this dual Sierpinski carpet, it's a different structure, but it has the same fractal dimension as the Sierpinski carpet. But it's very nice because it will allow us, by looking at the gasket and the carpet, I can see the influence of dimensionality. And by looking at the 2 different carpets, the carpet and the dual carpet, I have the same dimensionality, but a different structure, different distribution of voids, different level of lacunarity. And this is going to turn out to be also important. Okay, so let's take the Sierpinski gasket. You inject light here in the upper point, and you see how it propagates. You will make lots of different setups, more than 70, okay, with different length scales to probe it at many different lengths or times. And then you look at the variance in a log scale as a function of the log of the time or the log of the length of your waveguide. And now when you look here, you see something very interesting. First of all, it's not z square. Second, it's not linear in z. But you see that it starts with an exponent 2.5. At a certain point here, it's a length 2.675. It changes into something else. And from that point on, it is, look at it, 1.58. That's the slope of the green line, which agrees extremely well with the experiments and with the simulations. So the photonic wave function knows about the fractal dimension, and it knows it already very fast. Look at it. What are these magic lengths, 2.675 or 3.875? Well, what we see is 2.675, it's when the light started propagating. It thinks it's a continuum medium. When it gets at 2.675, it finds the first void. So the dimensionality gets lowered. And then it starts exploring around. And at 3.875, you see it went around. From that point on, the light already knows it is a Sierpinski gasket. Isn't it amazing? And then it immediately picks up the 1.58 dimension. That is the fractal regime. And then there is this other magic point when light came to the boundary, so it has explored the entire triangle, the mean square displacement or the variance starts to saturate. So there is a very clear fractal regime here in between where the light is seeing the voids in the material. And what's quite interesting also is that the mean square displacement is scaling with t to the fractal dimension only. And this is very different from the classical case where it scales with the spectral dimension divided by the fractal dimension. So it's clearly quantum walk. So now let me show you why you get the z to 2.5 here instead of the ballistic z square that you might have been expecting. If you would take a full triangle without any voids, and you would put the light here and see how it spreads, it would fully spread with z to 2.5. So it knows the boundary. This 2.5 is because of the boundaries of the triangle. If you would inject light in the center of a very big triangle and you let it diffuse, it would go with t square, z square or t square, okay? Until it finds the boundaries. But since you have to make your input at the edge, because this you want afterwards to have this part void, so you will see the finite size effects from the beginning, and this gives you a 2.5. So indeed, this 2.5 is the same in the fractal until it finds the first void, and afterwards it's just governed by the fractality. Okay. Here you can see on top how it spreads in a normal triangle, completely filled one, and the equivalent times in the fractal. You see, when it meets the hole, it gets there, it gets stuck. And that's when it starts changing the fractality. We can also characterize the quantum transport by a different quantity, which is the so-called Polya number. And the Polya number is an interesting number that is connected to this P11. You remember, this is the probability connected to the modulus in front of a certain site. And the P11 is the so-called return probability. So if there is a certain time when you return to the position where we injected the photons, this probability is 1 at a certain time, and 1 minus 1 is going to be 0, so the Polya number is 1. Polya number is 1 means at some time the photon goes back to the initial position where it was injected. And if it is 0, it means it never goes back. So if you now look at the Polya number, you will see something quite interesting. You see, this now has some structure, and if I zoom in the part which is here hashed, you see here inside the inset, there is a plateau. In the plateau, the center of this plateau is precisely the point when it started here entering into the fractal dimension. There is more structure there. This is the simulation, this is the experiment. So the Polya number is also seeing the signs of fractality. If you would have had the Polya number in a full, completely filled triangle, it would be featureless, just flat, growing ballistically. So it grows here and then it just gets flat, okay? So there are all these rich physics that are also characteristic of the fractals. Now, let's look at the Sierpinski carpet. What should change when I look at the Sierpinski carpet? Here is the variance. So first of all, now it starts with the 2.4 instead of 2.5, slightly different. And then at this number, 5.95, it enters the fractal regime, which is now 1.89 instead of 1.58. And which are these magic points down there? Well, these magic points are, as guessed, it starts deviating from 2.4 precisely when it meets the hole. And then it starts exploring around the hole and, oh, sorry, still there. It starts exploring around the hole and look here, it knows that it can come down again it knows it's a Sierpinski carpet, 5.95, and then the slope is the dimensionality of the fractal. So now, if you would inject light here, and now you have the boundaries which are slightly different for the square. If you calculate in the simulation how would be the slope in a completely filled square, it would be z to 2.4 everywhere. So we can perfectly understand how it starts. Let me get back here, how it starts with 2.4 and then it goes through some crossover and it gets into the fractal regime. Okay, so very nice. Here it doesn't saturate because the system to saturate, you see, it's enormous. It's a very big system. You would need to go with up to much longer times before it would saturate. Okay, now we understand it's picking up the different dimensionality. Here you can see again the same plot in the filled square and the same times how different it is. It can't go to the center. So this square here is just the little square here on top, okay? When it can go to the center, it will concentrate on the center, and here it got stuck. It has to go around. It keeps trying to find a way to go through the hole until it will find eventually and picks up the fractal regime. Okay, now, again, if I go into the Sierpinski carpet Polya number, I will see beautifully again the plateau centered around the 5.95, which is the point where the fractal regime is entering. And I can even see a bit more of structure over there. Very different from the usual square if I would have no holes. Now let's go to the dual Sierpinski carpet. Surprise, surprise. You get fractal from the very beginning, 1.89. Here is the simulation. And why is it so? Well, look at the holes. Here, you inject here. When you come to the second site, you already see that you can't hop to the middle because there is a void. So it is perceiving the holes from the very beginning. So there is no regime where it thinks that it could be a normal lattice. It is a fractal from the very first site. That's why you only have the 1.89. And then when it has explored the entire crystal, you will get a saturation, okay? Again, in the Polya number, we see all this beautiful structure agreeing completely with the features we are seeing here. So I come then to my conclusions. I think I am approaching the time. I have been showing here how to measure quantum transport in 3 different fractals based on continuous time quantum walks. We could directly observe the evolution patterns of the light in the fractals, and we could characterize the transport based on the variance and on the Polya number. And both features confirm that we have non-classical features, be it on the exponent of the mean square displacement, which is just the fractal dimension and not the spectral dimension divided by the fractal dimension, as in the classical case. And we can see it also in the manifestation of plateaus in the Polya number, which agree with the regimes where we enter the quantum fractal regime. We could observe transitions from normal to anomalous transport, depending on the type of the fractal that we have. And we could single out the influence of the geometrical features and how the presence of voids are going to influence what we are going to see. So with that, let me just acknowledge the senior collaborators. You have seen already some of them. So for the STM, Daniel van Mackelberg and Ingmar Zwart, and for the photonics, Chanmin Jin, who is the professor leading the photonics lab in Shanghai. And let me show you some faces of the PhD students. The group is much bigger, but I will show you just two of them here who did some of the works that I have shown for the STM. Sander did most of them, and yet some of them. And the experimentalists Marlou and Sarsha for the experiments on the STM, Xiaoyun Chu for the beautiful measurements in the photonic lattices, and Robin and Ozella, Robin is a master student, that Ozella, who is a PhD student, is co-supervising with me. Unfortunately, I didn't manage to come up to their topic. They are doing fractional calculus, and we have been just finding a time glass in a fractional Langevin equation. So with that, I want to tell you that there is plenty of room at the bottom, as Feynman has been suggesting us to build structures in a bottom-up approach, but even more in a fractal. And I thank you very much for your attention.
So thank you very much, Cristiane, for the really fascinating talk. We have a number of questions that have come in, and so we'll try to get through a few of those now. And again, as Sebastian said at the beginning, any that we don't have time for, Cristiane has kindly agreed to answer in written form that we'll post on the website. So the first one of these sort of refers again back to this this really nice random triangle game that you had in the first part of your talk, Cristiane. So this question pertains to the fact that, that you've shown from a random game that you get a regular structure here in the sense of a fractal. But we know, of course, that there exist also regular games that give you a random complex structure, such as cellular automata, whose dynamics in that sense are then hard to invert. But the question is, for the game you sort of showed us and for that general class, is that also the case, that you can have you know, similar situations where maybe the situation is the process is hard to invert, and does that inversion then depend on the game that you play?
Yes, so this is actually a very interesting question. Misha Katznelson in Nijmegen is now trying to categorize disorder with some number. He's trying to find numbers which would be a measure of disorder. And I think the next step will be to understand how this connects to multifractals and how this connects to fractals, to try to understand a deeper connection between what we think that is disorder or laws that we give a certain rule on how to construct something, and by looking at it at certain times, it looks like it's random, but there is an inherent order emerging out of it. So we are just starting with these studies. I find it absolutely fascinating. We are also investigating to give you an idea of the areas I am going through that with another master student and also with a Sander, so Anwar Mustaj and Sander. If you have a Fibonacci chain and you put disorder, the spectrum is fractal. What happens to the disorder in this fractal spectrum? How does it manifest? And there is order in it, and you can find the order through randomicity. So I think this is a field that is just starting, and there is a lot to come still. I am very curious about it.
That's fascinating. Thank you very much, Cristiane. We then had we have a series of questions sort of a little bit more about the experimental side, but also asking about the difference between looking at sort of photons in the quantum regime and something that would be more of a classical light propagation. So the first of these is one that's come in from two different people, including Alejandro Gonzalez Tudela in the chat. You see here quantum, and equivalently, what sort of intensity light do you have to work with so that you would see this as quantum transport rather than a property of classical light? Or can you distinguish the two in this regime?
Yes, so maybe I don't know if Shanmin Jin is there. He could take the microphone if he wants to say something about that. That is always, of course, a big issue that people say, well, how much is this really quantum? It's single photon regime, I have to say. It's not multi-photon, it's single photon, as we had also single particle regime when we were looking at the fractals in the STM structure. But you can see it is overlap of wave functions, that it goes from one side to the other via wave function overlap. So in that sense, it's quantum. It's governed by a quantum equation. And it, as you can see very clearly from the diffusion, it obeys completely different laws in comparison to the classical laws. So I would say it is quantum diffusion, although it's single particle wave function, it's single photon. I don't know if Shamin is there and if he wants to add something.
Okay, I think we'll just move on to the next question at this point. And of course, if you have something to add or your collaborators do, again, we'll be asking these questions in written form, and you're welcome to add some things to that. So the other sort of related question came from Didi Leibfried. Again, that is, in these experiments, do you have to account for loss of photons when you're calculating things like the Polya numbers and so on?
Oh, I will not know the answer to this question. So the Polya number also is, I don't think so, though, because it is also calculated numerically and it's agreeing pretty well. So I don't think that there are losses being included there, but I am not 100% sure. And if the answer is different, I will post it. Okay? Okay,
that sounds great. And then maybe just to finish up, because we're just sort of starting to run out of time, there were a couple of questions about, you know, the relationship between sort of seeing sort of the fractal structure or the behavior and what happens if you change things sort of in the underlying Hamiltonian. And there are sort of questions that go in two directions. One of them in the chat, that if the waveguides were not arranged in a perfect fractal pattern, would you see some signature of localization or something like that? And then maybe turning that around, a question from Callum Duncan, where he asks if there's an example where the underlying Hamiltonian has a fractal structure, but the wave function, in contrast to the ones you've shown us, doesn't gain that fractal structure.
Yeah, so can't answer this question yet. We are running the simulations now. If you would take the perfect triangle with no voids, and now if you would create a little void outside which doesn't obey the fractal dimension, what would you get? I don't know. We are running it right now. So we are running several simulations to understand if you have little voids in a disordered manner, 1 or 2 or 3, how is it going to behave? So we had to finish the work first, and now we are thinking of all the additional questions that might emerge. I might have an answer for that. So Xiaoyun is now running the simulations, probably in a week or so. We could tell you more about that. Just drop an email.
Great. Well, look, thank you very much again, Christiana, for your answers to these questions. Again, if people have additional questions, feel free to send an email to Quantum Science Seminar. We'll pass this on to Christiana and she'll give us answers in written form to the rest of those. But again, thank you very much for the fascinating talk, which I've enjoyed very, very much. And I'll pass back to Sebastian for the final word.
Yeah, from my side also, thank you very much, Christiana, for a great talk. And I would like to remind you, all of you, that next week is the week where DAMOP, the APS division of Atomic, Molecular and Optical Physics, has their yearly meeting. And of course, this year it's not happening in person, but they opened it up for everybody. It's free for everyone to access online. So there will be very many talks, very many poster sessions that you can look at. And for that reason, we're not going to do a quantum science seminar on June 4th. You should certainly check out DAMOP. There's many of our viewers, I'm sure, will be presenting there, so please have a look there. 2 weeks from now, on June 11th, we will have a seminar by Thierry Giamacci, and he's very likely going to talk about one-dimensional systems. We're very excited to hear about what's going on there. And tomorrow, you should also check out the AMO seminar, where Jeff Thompson will be talking about another solid-state system of rare earth ions embedded in a solid-state matrix and doing AMO science with that. With that, I would like to thank you for your interest again and hope to see you again next week. But first, let's maybe try again to share our screen here, see if this is going to work. Let's see. Because we do have quite a few other attendees that more than typically. And there you go. So everyone here, say hi. And thank you again. I'll see you next week, same time, same place. Bye.
Bye. Thank you.